Hello and good day. My name's Stanley Mordensky. I'm a Mendenhall Research Fellow with the U.S. Geological Survey. I work with Eric Burns, John Lipper, Jacob D'Angelo, and Carrie Lindsay as part of the Geothermal Machine Learning task. For the better part of the last year, our team has been developing data-driven, that would be machine learning, modeling methods for geothermal resource assessment, and that is precisely what I have the privilege of sharing with you today. However, before we dive into those details, allow me to share a quote with you from Richard Hamming. The purpose of computing is insight, not numbers. And that idea is at the heart of our working philosophy. Start simple, understand why and how models are producing their predictions, and only then systematically increase the model complexity. Why spend so much time trying to understand how models function? Why make the effort to recognize their nuances? The thing is, by this point in time, the overt expressions of geothermal activity, such as the erupting geysers in the image before you, those have been found. Now, we rely upon more subtle means to identify the more subtle resources. We've developed machine learning approaches to produce data-driven geothermal favorability models. We compare these models and their results to a previous geothermal resource assessment, that would be the 2008 USGS resource assessment, that relied upon modeling which required more user input, that would be expert decisions. Doing so allows us to define a baseline for geothermal machine learning models, from which we can then build complexity. In 2008, the U.S. Geological Survey completed its moderate and high temperature geothermal resource assessment of the western United States. That assessment used two methods, that would be weight of evidence and logistic regression, to create a series of favorability maps. We used the same data from the 2008 assessment in the training of our models used for the comparison with the models from the 2008 assessment. Through that comparison, we make some key findings. The 2008 Geothermal Resource Assessment was dependent upon expert decisions in how to process the data. These expert decisions transformed the otherwise linear methods into nonlinear methods. Lastly, geological data sets are large, complex, and not necessarily compliant with existing forms of traditional machine learning. If we are not careful with how we use our geological data, it is easy to break machine learning methods. We must be careful. Before going into too much detail on the machine learning algorithms and their results, let's spend a minute talking about the 2008 Geothermal Resource Assessment methods and the expert decisions upon which they were dependent. The 2008 Geothermal Resource Assessment used 5 input features, rather some combination of 5 input features: heat flow, distance to a magma body, distance to a fault, horizontal stress, and seismic event density. A grid of over 720,000 cells was then created for the western United States. Each cell contained the input feature values as well as a label of geothermal system or no geothermal system. Using these input features and these labels, each cell served as a sample to produce and train the models for the 2008 Geothermal Resource Assessment. Expert decisions became involved in the 2008 Geothermal Resource Assessment through the handling of the input feature sets. Specifically, due to the tools available at the time, these input feature sets, which had continuous ranges of values, had to be binned. These bins were then used as the input values for the 2008 Geothermal Resource Assessment. The methods consisted of weight of evidence and logistic regression. For the safety of the audience and myself, I've been advised to avoid as much math as possible in this presentation. However, what I wish you to understand in the case of weight of evidence is that for every bin, for every feature set, a weight value was assigned depending upon the correlation with known positive labels. Then the corresponding weights and bins are summed per cell to provide a probability value for every cell. In logistic regression, a logit function transforms those bin values into probability values. Now that we've taken the time to understand the 2008 assessment, let's turn our attention to the machine learning approaches. Machine learning has many different meanings to many individuals, and that's because machine learning encompasses a wide range of disciplines. When I say machine learning in the context of this study, I'm referring to a specific type called supervised machine learning, and not just supervised machine learning, but classification. Supervised machine learning refers to the fact that with our data, we're using labels, that would be geothermal system, no geothermal system for each cell, to train our classifiers. The classification component of our machine learning refers to the fact that we're not trying to regress a series of values from the input features, but instead simply trying to say geothermal system, no geothermal system. Specifically, we use three machine learning approaches to train data-driven classifiers from the 2008 geothermal data. The first of which is logistic regression. Yes, this is the same logistic regression as the 2008 assessment. However, in the 2008 assessment, the data were binned, whereas with the machine learning approach, the logistic regression algorithm allows the continuous range of data to be used. What that means is that the machine learning logistic regression removes the expert decisions and instead allows logistic regression to behave as a data-driven algorithm. By choosing logistic regression as a machine learning classifier, we can compare the effects of expert-driven decisions and data-driven decisions directly. We also use support vector machines and XGBoost. To give you a conceptual understanding of these two different types of algorithms, understand that support vector machines operate by plotting the data to a dimensional space equal to the number of input features. In the example before you, we have features x1 and x2, along with two labels of data, the blue circles and the hollow circles. A decision boundary is then drawn between the labels. XGBoost, at its heart, is a series of simplified decision trees. Each decision tree is built upon the last to better fit the data. The final leaf of each tree provides probability value. Probability is determined by the summation of all these values across all the trees. By including support vector machines in XGBoost, we introduce a new type of classifier to the geothermal resource assessments. Specifically, we're introducing the concept of nonlinear classifiers when only linear classifiers had been used in the past. A linear classifier is, by definition, a classifier that uses consistent weighting across the entirety of the data set with the model. Whereas nonlinear classifiers change how they treat the data depending upon other aspects of the values of the data. The nonlinear classifiers might have a potential advantage over the linear classifiers. What if geothermal systems are most amenable to a specific range of a feature's values, for example, seismic density? We don't want that feature to be too large or too small, but instead we need a Goldilocks zone per se. Nonlinear classifiers have the potential to target that specific, perhaps narrow range in feature values, whereas linear classifiers cannot. We use the data from 2008 with these machine learning approaches to create data-driven classifiers. However, as we began the training process for these machine learning classifiers, we quickly realized that we had some challenges as a result of the data itself. Specifically, we were working with positive unlabeled data. Positive data being positive labels on the cells, that is where a geothermal system is present. Unfortunately, we don't have no negatives. Instead, we have areas where geothermal systems may or may not be present. Then we have class imbalance, and we don't just have minor class imbalance, we have extreme class imbalance. Class imbalance is defined as having a disproportional relative quantity of the label types. Class imbalance is defined as extreme as low as a 1:10 ratio, or much less a 1:100 ratio. We're working in far excess of that. Our class imbalance is a positive unlabeled ratio of 1 to roughly 2,600. To address the positive unlabeled quality of the data, we try two versions of custom written train test splits when training and producing the models. The details of these train test splits can be found in the accompanying proceedings paper. For the context of what I share with you today, it is important to only understand that there are two versions of the train test split that I refer to as single and ensemble. In the single version, or the single strategy, a single model is trained and evaluated during the training process. With the ensemble strategy, several smaller models are trained before evaluation, and these models are averaged together for the evaluation process. To address the positive unlabeled quality of the data, we use an F1 score as the evaluation metric. An evaluation metric is a way for a machine learning algorithm to assess how well it's learning the data. And there are different evaluation metrics, such as accuracy, precision, recall, and then the F1 score. The F1 score is rather unique in that it considers true positives, and false negatives in its evaluation. And previous positive unlabeled research has found the F1 score to be most appropriate for that type of data. To compare these algorithms, we first used the methods from 2008 along with the 5 feature sets we've discussed to produce favorability plots. We then do the same with logistic regression, support vector machines, and XGBoost, using the 2 versions of the custom test train split. When looking at these 8 plots of geothermal favorability, some important distinctions can be made. The first of which is that areas with expected high geothermal favorability consistently agree with one another. For example, Yellowstone, the Salton Sea, the geysers, the Great Basin. The second regards the 2 versions of logistic regression, specifically the expert-driven logistic regression and the data-driven logistic regression. The expert-driven logistic regression has stark contrast between different regions in terms of geothermal favorability. Juxtapose that stark contrast in the 2008 logistic regression to that of the modern data-driven variants of logistic regression, where instead we see a gradual change in geothermal favorability as we move across any region in either versions of the train test split. So why do we see this difference between the 2008 and the data-driven versions? The answer lay in the fact that the data for the 2008 logistic regression had to be binned before that method could be applied. In so doing, that continuous data being binned turned an otherwise linear method into a nonlinear method. The same can be said for weights of evidence. Next, although areas of high geothermal favorability are consistently predicted across the 8 different methods, areas of low favorability, rather where the lowest favorability is found, vary substantially between the different methods. That is, the greatest variance we see amongst these methods is not with predicting high geothermal favorability, but with low geothermal favorability. Finally, it appears that XGBoost has the greatest granularity out of the different approaches considered, including that of the 2008 methods. For every combination of a machine learning algorithm and train test split strategy, we completed 100 unique train test splits to produce 100 different models. Here, we report the F1 scores for the 100 test train splits from every combination of those strategies and classifiers. In general, a higher F1 score means a better performing classifier. And logistic regression, either the single variant or the ensemble variant, both produce the highest F1 scores. Conversely, both strategies with the support vector machines produced the most conservative algorithms, and by conservative, I mean that they were the least likely to predict favorable geothermal conditions. For practicality's sake, I would like to note the differences in training speeds between the different strategy algorithm pairs when training on a personal computer. The training time for the strategy algorithm pairs varies by several orders of magnitude. Another way to compare the different models is to use crossplots, and here we have exactly that. Between the 2 axes, we have a cell-by-cell comparison of the geothermal favorability values of the 8 assessments considered in this study, with -5 being low geothermal favorability and 5 being high geothermal favorability. At the intersection of the same models, we have a histogram of geothermal favorability values. Given that these geothermal favorability values have a normal score transformed, These histograms should appear to have a normal distribution. However, some of the histograms appear quite distorted, particularly the histograms from the 2008 Geothermal Resource Assessment, where instead of seeing a standard histogram, we see spikes. These spikes are, again, a product of the binning of the otherwise continuous data in the 2008 assessment. We also see spikes in XGBoost. This is due to the data-driven binning of the algorithm. Where we have spikes in the histograms with the 2008 methods and XGBoost, we have gaps in the crossplots. These gaps, again, are a product of the binning of the data. We use root mean square error to provide an empirical basis to compare the variance amongst the classifiers. A higher root mean square error on these crossplots means that, in general, the two classifiers disagree about the predicted favorability for the cells in question. In general, it appears that either version of XGBoost contributes to the greatest root mean square error. However, we note amongst all the classifiers that the greatest disagreement between predicted favorability values occurs at lower geothermal favorability values. At higher geothermal favorability values, predictions appear to become more consistent across the classifiers. We saw this exact behavior in the favorability maps that we inspected a minute ago. These crossplots, however, raise new questions. For example, given that variance between them is less at high geothermal favorability than low geothermal favorability, could we combine these different classifiers to create a more conservative classifier at high geothermal favorability? Similarly, would root mean square error at a certain favorability threshold, say above a normal score transform value of 0 or 1, be more effective at comparing the performance of these different classifiers than the root mean square error of all the geothermal favorability values in the mapped area? In addition to these questions, we have other pursuits, such as developing new feature sets. How do we consider aseismic deformation or the interaction of faults? What about permeability? Just as importantly, how do we gauge feature importance as we add new feature sets? Then there's the concept of geophysical provinces. Should we expect systems in, say, the Snake River Plain to match those of the Cascades or the Great Basin? Or do we have multiple types of positives? Might we have multiple types of negatives? How can we use confirmed negatives? What about developing a novel performance metric? How can we better handle the extreme class imbalance? That brings us to the end. We chose to use the limited data from the 2008 assessment for this analysis for a couple of reasons. Foremost, these data allow us to develop an understanding of how the machine learning algorithms compare to the geothermal data, as well as to compare data-driven machine learning algorithms to those that require expert decisions. That is, this analysis serves as a baseline. Now, when we add new datasets collected since 2008, we can assess the value these new datasets add to predictions. This analysis also helps us to understand how expert decisions affected the predictions in the 2008 assessment. Specifically, in the 2008 assessment, expert decisions turned otherwise linear methods nonlinear. We also see how the predictions from all the different approaches compare against one another. And we find that low favorability regions predominate the variance between classifiers. Between linear and nonlinear classifiers, the nonlinear classifiers appear to be the most conservative. This is a result of the linear classifiers treating the input feature data with constant weights, whereas the nonlinear features emphasize different feature values from different datasets depending on the other feature values, thereby allowing the nonlinear classifiers to better target the seemingly perfect conditions required for a hydrothermal system. Lastly, we are reminded that geothermal and geoscience data in general hold implicit challenges when working with machine learning algorithms. We should exercise caution when using these methods. I thank you for your time and would be happy to answer questions if you wish.